So load flow analysis, it requires us to solve the power flow equations, right, that we saw in the previous lecture. Now the power flow equations, these are non-linear algebraic equations. Okay. Now if a linear equation is given, then it is easier to solve, but when a non-linear equation is there, then how do you solve? For this you are going to use the iterative methods are required to solve these equations. Okay. So that is what we are going to do now. First method that we will see is the Gauss-Seidal method. From the gate perspective, actual solving of the equations using the iterative methods is not very important, but you need to know what the method is, how it is done. Okay. So we will discuss the various steps involved here. The first step in Gauss-Seidal method, it is to number the buses. Okay. Numbering of buses. So usually what we do, like discussed before, the slack bus, it is numbered as bus 1. Next, PQ buses are started from bus number 2 and then PV buses. So for example, if you consider n number of total buses, consider n number of buses, p number of PQ buses. That means out of n number of buses, p are PQ, okay, and q number of the n buses are PV buses. Okay. So PQ bus, if you start from numbering from 2, then till it will extend till p plus 1, because there are p number of PQ buses, and PV buses, it will now start from p plus 2 to the total number of buses, that are n, right. So this is how you number. The second step is to form the admittance matrix. So it will be easier if you can express the admittance in both the rectangular and polar forms. Okay. So this will be easier when you are doing the calculations. Step 3, here we are going to assume some initial values. Assumption of initial values. So what are all the parameters that you have to assume? The first one, for PQ buses, here you have to assume both the magnitude and the voltage angle. Now what are the initial values? We are going to take the initial value of magnitude to be 1 per unit. We are going to take the per unit values, and delta, usually you take it as 0 degrees. If you assume like this, then it is usually termed as flat voltage start. So this is the usual assumptions. It will be easier. Now the second one, for PV buses, you have to assume the voltage angle. Here also you are going to assume this to be 0 degrees. Okay. So here you can see that in PQ buses, neither the magnitude nor the voltage angle is known. So we are assuming those values. And in PV bus, we know the voltage magnitude. So we are only assuming the voltage angle. Okay. So these are the assumptions. Step 4. Now we are going to start the iterations. First we are going to start the iterations for PQ buses. Okay. So find voltage, both magnitude as well as angle of PQ buses. So how you are going to find this? If you remember the expression for injected current at ith bus, okay, current injected at ith bus, it will be equal to yi1 v1 plus yi2 v2 plus so on till yii vi plus so on till yin vn. Okay. Now this term yii vi, okay, so we want voltage at the ith bus, right? So this term we will take to one side and all other terms we can write on the other side. So this is equal to II minus sigma j is equal to 1 to n, and also j is not equal to I. Okay, so all the terms except the value where j is equal to I. So the summation of all such terms Vj. Okay, so what will be Vi? This is now equal to 1 by Yii II minus sigma j is equal to 1 to n, and j is not equal to I, Yij Vj. Okay. Now here what do we know? We know the admittance anyways, we know from the admittance matrix. Okay, and these voltage values are nothing but we have assumed all of the voltages for all of the buses, right? Here all of the buses are included except the ith bus. Okay, so we have assumed all of these voltages, so we are going to write those assumed values. Yii also you know. The only thing is the current, injected current at the ith bus we don't know. Okay, so what we are going to do, we are going to express this in terms of the real and reactive powers. So what is Vi II bar conjugate? This is equal to Pi plus jQi, right? The real and reactive powers at the ith bus. So now if you take the conjugate, then this Vi conjugate into II bar is going to be Pi minus jQi, right? So II you can write as Pi minus jQi divided by Vi conjugate. So if you substitute in these values, all you know, right? Pi, Qi, II. For PQ bus, you know all of these values. So the final expression, you are going to get the voltage at ith bus is equal to 1 by Yii Pi minus j Qi divided by Vi conjugate minus sigma j is equal to 1 to n, and j is not equal to I, Yij Vj. Now this is the general expression that we use for iterations. Okay, in order to understand more clearly, you can write it in this manner. The first iteration we will write as a superscript 1. Okay, so this will be equal to 1 by Yii Pi minus j Qi Vi 0th value, that means the initially assumed values. Okay, so this conjugate, okay, minus sigma j is equal to 1 to n, j not equal to I, Yij, similarly here also Vj of the 0th iteration, that means the assumed value. Okay, so this is how you find out the voltage of the bus at the first iteration. Okay, you are going to do more iterations, so I will write the general expression that we use for rth iteration. In general, for rth iteration, you are going to get VIR is equal to 1 by Yii Pi minus jQi. Everything is same except that here in place of voltage you are going to write the r minus 1th iteration. Okay, this will be conjugate minus sigma j is equal to 1 to n, j not equal to I, Yij Vj r minus 1th iteration. Here there is one more thing you can do to fasten up the iterations. So if you understand, well and good. If it is getting confused, don't worry, you don't have to remember it. Here you are writing r minus 1th iteration, right? Now let us say you are finding the voltages from buses 2 to p plus 1, right, for the PQ buses, right? Now let's say the voltage at bus 2 you have already found out. Okay, then next you are finding the voltage at bus 3, so I will be equal to 3, let us say. Okay, now here when you are this summation, when you are doing, the bus 1 also will be present, bus 2 also will be present. So the bus 2 rth iteration you already know. Okay, so you can write down, instead of r minus 1th iteration, you can write the rth iteration of the second bus voltage. but the voltage is beyond bus 3, those you will not have the rth iterations, right? So those you can write the r minus 1th iterations. So this is just to fasten up the iterations. There is another way, which is the acceleration factor, so that we will be discussing a bit later. So you can in fact write this down also. Vi of r is equal to 1 by yii pi minus j qi divided by vi r minus 1 conjugate minus, from j is equal to 1 to I minus 1. You will have the rth iterations. So yij, vj, rth iteration, okay, minus from j is equal to I plus 1, ith bus is not included. So I plus 1 to n. This will be the r minus 1th iterations, okay. So this slightly modified expression, it is for faster convergence. Now once we find out these voltages for each of the PQ buses, then what you have to do, you have to check whether the calculated voltage, it is within the specified limits. Sometimes the minimum and the maximum value of the voltages that is allowed at the bus, it will be given, okay, and the calculated voltage, it should be less greater than minimum voltage and less than the maximum voltage. It should lie in between these two values, okay. So in case of a violation, then what will happen? If the calculated voltage is greater than the magnitude, we are dealing with the magnitude, so it is greater than the maximum voltage, then what you have to do, you have to take the voltage to be equal to the maximum voltage, okay. And if this comes out to be less than the minimum voltage, then you have to set the limit, okay. You have to limit the voltage to the minimum value. So this is step 5. You have to repeat the steps 4 and 5 for all of the PQ buses, okay. So that means, let us say second bus you are finding the voltage, then you will do step 4 for the second bus and you will check the limits, that is step 5, and then you will go to bus 3. If it is a PQ bus, then you will again do step 4, then step 5, okay. So you have to continue like that for all the PQ buses. Once PQ buses are completed, then we have to go to the next step, which is step number 6. Step 6. So next we are dealing with the PV buses now, okay. You have to first find out the reactive power of the PV bus. PV bus or the generation bus. So we know that the reactive power, it is equal to the imaginary part of the complex power. That means imaginary part of V bar I bar conjugate, okay. Or you can also write as minus of imaginary part of V bar conjugate I bar, okay. So now instead of I bar, you can write the expression in terms of admittance and the voltage, okay. So from here you can get the reactive power at ith bus as minus of imaginary part of Vi conjugate into sigma j is equal to 1 to n y ij v j, okay. So instead of the current, we are writing the expression in terms of this summation. So for an ith PV bus, the rth iteration, this is all iterations only, right. So the rth iteration, it is going to give you Qi of r is equal to minus imaginary part of Vi r minus 1th conjugate, okay, r minus 1th iteration of voltage you have to take, into sigma j is equal to 1 to n Yij Vj r minus 1th iteration. And also, just like in the case of voltage, you can write the rth iteration as minus imaginary part of Vi R minus 1 conjugate into, here you can divide from j is equal to 1 to I minus 1. Here you are going to get Yij, Vj, you are going to get rth iteration, right, plus sigma from j is equal to I to n. You will only have r minus 1th iteration. So this is Yij, Vj, r minus 1. So this will be the expression for faster convergence. Next, step 7. So here also we are going to verify the limits. Okay, if the calculated value of the reactive power, it comes out to be greater than the maximum value, then you will have to limit the value of Q to the maximum value. Okay, and if this comes out to be less than the maximum value of reactive voltage, then this you have to equate, Q is equal to Q minimum. Okay, but what is happening in both these cases, the reactive power we are giving it a constant value, right? So it is no more a PV bus, it will become a PQ bus. The bus should now be treated as a PQ bus and not a PV bus anymore. Okay, because the value of Q is now fixed, it cannot be changed. Okay, so the value of Q, if it is fixed, it means it should be a PQ bus. So now if it is a PQ bus, then what you have to do, you have to now find out its voltage, right? So in either of the above cases, voltage has to be found from steps 4 and 5. Okay, but if there is no violation, then you can proceed to the next step. If there is no violation of the limits, then we proceed to the next step, which in this case is step 8. Now step 8, you have to find out the voltage angle, right? In PV bus, what else is left to find out? We have found out the reactive power, so voltage angle is left out. Okay, so find voltage angle of the PV bus. So what is the equation that we are going to use? The same equation that we have used for PQ buses, right? When finding the voltage for the PQ buses. So what was it? Vi of R, this will be equal to 1 by Yii Pi minus jQi divided by Vi R minus 1th iteration conjugate. Okay, minus sigma j is equal to 1 to I minus 1 Yij rth iteration of Vj minus sigma j is equal to I plus 1 to n Yij Vj r minus 1. This is the expression. Here you will get the voltage, and if you get the angle of this voltage of the rth iteration, then you are going to get the required angle, rth iteration of the delta. So then for the next PV bus, you have to go back to the step 6. If there are more PV buses, go to step 6. But if all of them are complete, then go to the next step, which is 9 in this case. Now what happens in the 9th step? Till now you have found out the voltage values for all the PQ buses and the reactive power and voltage angle for the PV buses. Okay, now you have found that for all of the buses. One iteration is complete, first iteration is complete. Now what you have to do, in step 9 is you have to verify what is the difference between, if you're taking the voltage, what is the difference between the rth iteration and the r minus 1th iteration. And if this difference, it is very less, that means what? Both the iterations, both the values, they are equal, right? So if they are very less, then you can stop the iteration. So if it is the first iteration, then VIR minus 1 will be the assumed values. Okay, and if it is the second iteration, that means if this is not a very less quantity, then you have to do the iteration again, right? Then it will be, let's say this is second iteration, then this will be the first iteration. So like that you have to find out the difference between two consecutive values of iteration. Okay, sometimes this value will be given, this difference, it should be less than a certain value so that you can stop the iterations. So that also sometimes it will be given. So here you can write down, if difference between two consecutive iteration values is greater than a specified tolerance, then repeat steps 4 to 8 for only those buses. So here you can add of any bus. Okay, so that means when you are checking out the difference, for some buses the tolerance may be exceeded, for some it may not be exceeded. Okay, so wherever the consecutive values, the difference between consecutive values is much larger than the specified value, then you have to repeat the iterations. Now after doing enough iterations, there will come a point wherein it will be, the difference between the two consecutive values will be less than the tolerance value for all the buses. Okay, so you can write here, once the difference is less than specified tolerance for all buses, then you can stop the iterations. And then we have to go to the next step. So in the next step, it is nothing but we are finding the power and the reactive values and the currents, whatever information that is required, right? So step 10, calculate P and Q for all the buses. So you are going to get the injected and the delivered power, active and reactive power. Okay, so this is how you get the load flow solution. How will you find out this active and reactive power? Using the power flow equations, right? Now that you know the voltages at each and every bus, you can use the power flow equations to find out P and Q. Finally, one last step you have, which is to calculate the injected current. Okay, so this is going to be current flow from bus I into transmission line connected between I and J buses. So let us say transmission line IJ. So this is going to be IIJ is equal to VI minus VJ into admittance YIJ plus also VI YIJ naught. So this is the admittance from the bus to the ground. Okay, so this is how you will be able to find out the injected current. You can also see it as a diagram. This is bus I and this is bus B, let us say. Okay, so here you have the transmission line whose admittance is YIJ, and you can also represent this as YJI. Okay, and here you have the shunt admittance. This is represented as YIJ naught. Similarly, you may have a shunt admittance here, and this you are going to represent as YJI naught. Now the current Ij is going to be flowing here. In the same manner, if you take the current Iji, this also you can find out as the sum of this current and this current. The expressions will be slightly different. Here you have written Vi minus Vj, but if you are taking from this in this direction, it will be Vj minus Vi into Yji. Okay. And next is the complex power. Complex power from bus I into transmission line Ij. What is this? Sij is equal to Vi Iij conjugate. So that is how you have to do the Gauss-Seidel iterations. But one disadvantage of Gauss-Seidel method, it takes a lot of iterations, number of iterations we need to finally be able to get the required solution. Okay. So one thing that is done here is we make use of something called as acceleration of convergence. This is denoted by alpha. So what is this alpha? Usually it is taken as 1.6. Usually this value is 1.6. So how we use it is the rth iteration of voltage, VIR. Okay, so this you can write in the accelerated form. So the accelerated form of the rth iteration will be equal to whatever calculated value of the rth iteration you are getting, plus alpha into Vi of r minus Vi of r minus 1. Okay. So it's simple, nothing. You are finding the voltage at the rth iteration, right? Now what you are doing, you are finding an extra parameter which is equal to whatever calculated value that you got in the iteration plus this alpha into alpha is 1.6, the difference between the rth and the r minus 1th iteration. That's all, nothing else. So in this way what will happen, the number of iterations they can be reduced. So that's why it is called Vi rth iteration accelerated value. Okay.